Okay, people did quite well here. Okay. I asked to do this, and then I asked for the reasoning, but everybody wrote out the equation. Okay, so maybe in a little more detail than you gave, but I'm happy with what you did. Okay. Now a little more formula, so let X be equal 1 C2 C3. You decide representation, right? Then I'll put a number in. I'm not even going to put a number in because I'm not going to do the number. And this means that AFC can be represented as some of these multiples of the bases. Okay. And this implies short process, you know, if you write out the simultaneous equations, okay, and then represent the simultaneous equations as a matrix equation, you get a familiar equation. The left-hand side is just this matrix product. Okay. And this is what you call the P matrix. In the notation of your book, you don't necessarily have to use that letter. But since it's going to be used later in the text, and it's very important and fairly demanding, or fairly challenging context, okay, it probably would be best to use P just so you don't really have to think, what's that P thing again? Okay. Still, if you understand this, you can do it. So that your solution is the inverse of this matrix. Times you're given or you're given representation. But and then this is the representation you're looking for. So what it comes down to then is that we got P, that's B equals X. This, of course, assumes that P is invertible, but if this is a basis, then P is invertible, which I think we understand pretty well. To invert the matrix, you just do this. This is how you invert a matrix. Okay. Now, if you have a basis B and another basis B prime, you wanted to represent in terms of those bases, you would take the matrix with respect to P and the matrix with respect to B, matrix with respect to B as a matrix with respect to B prime over here, and you would reduce that augmented matrix. And it's fairly straightforward to understand why you do that, but I'll let you think about it, okay? So, as I say, everybody has the equation. Of course, the numbers are such that it wasn't all that simple to reduce, so it took you a while. I don't think anybody completely got to the inverse matrix. But yeah, make sure you're using the identity matrix with the P, so you understand how to solve the matrix equation this way. That's something that might have slipped by. You're not careful. Okay. You know, you just get into reducing the P matrix and forget that the I matrix ought to be there, so you never get an inverse. You don't want that to happen. Okay, well, that's very good. You'll do quite well. So, you took the Earth and put it in the blender, came out, you would have something about as dense as this. Now that's 2 kilograms. And this is what we're talking about, the brass weight, about 2 kilograms. It is 2 kilograms, very close to 2 kilograms. It's expensive because it's machined really closely. So that would maybe represent average Earth stuff, okay? And for that particular sample, that's about 20 moles. How many know what a mole is? Everyone has chemistry, right? Okay, and a mole contains approximately 6 times 10 to the 23rd atoms. And I think you all understand that because you all seem to be pretty well educated, okay? Mass of the Earth, about 6 times 10 to the 24th kilograms, which we figured out a long time ago. We refined it, but just by measuring the distance from the Earth to the Moon, which people did hundreds of years ago, based on eclipses, okay, based on what penumbra and on the Moon and stuff like that, how long the Moon was in shadow, and a couple of other things. Pretty impressive notion for 1600s. Okay, but by the fact the Earth takes a month, well, it takes as many seconds as it does to complete an orbit. It's pretty easy once you have Newton's law of universal gravitation to figure out the mass of the Earth. If the Earth was more massive, the Moon would go around faster. Less massive, go around more slowly because It's the centripetal acceleration, just like swinging a weight around on a string, that's supplied by gravity that pulls the moon toward the Earth, so the moon keeps curving in its orbit. Okay, some people say, well, it keeps falling, but it's moving at the speed that prevents it from getting any closer. One way to put it. And if you spin something faster, you have more centripetal force, right? Spring, it's more tension. Well, by that, you can figure out pretty closely what the mass of the Earth is. It's very close to 6 times 10 to the 24th kilograms. So, question, how many atoms are there in the Earth? Well, think about it for a second. Well, if you're tuned in, you say, well, we're going to multiply the number of atoms in a mole by 20 to get the number of atoms in a kilogram. Okay? Just like you multiply this number by 2 to get the number of atoms in that brass weight, assuming that that's about 20 moles. Fairly close. Okay? And then you'd multiply that by the number of kilograms, right? Okay? So that's pretty straightforward. The thing I did with my class was they started immediately writing down numbers. And nobody got it right. Some got parts of it, some multiplied this by this, and then they multiply this because they'd gotten a number and they were happy. Okay, or at least they thought they'd done something, and they had. It was appropriate. But to see what to do, I said, well, I want you to write down in words what you're doing. Okay? They had a lot of trouble writing down in words because all they'd ever done in math class is line calculation. Okay? Now, y'all have done better than that, obviously, because you're doing so well here. Okay? Still, there's something to be said for the idea that you write down what you do. Okay? And maybe just in words, the number of atoms in the Earth is the number of kilograms in the Earth times the number of atoms in the kilogram, right? And that's, yeah, so there you've written out what you're doing, and then you write the numbers, okay? Now, the analogy for this course is you maybe in the problem that we just saw, which again was this in terms of this. You didn't need to do it because you did it right, okay? If you're in something that you're not sure how to do, write out in words, okay? Well, let's see. This means that there's a linear combination of these that equals this. So that linear combination should give me an equation that I can solve and so forth, okay? Just whatever way makes it as clear as a bell what your strategy needs to be in solving the problem. And of course, you enhance that strategy by, reading some of the proofs, trying to understand the proofs that you see in your book, which are nicely presented, okay? And usually very elegant. So that's just a plug for thinking about what you're doing. And if you get a difficult problem, write out in words to clarify your thinking before you start doing a bunch of symbols and a bunch of calculations. That make sense? Okay, so again, you'd have no problem with that. If we went all the way to the number of atoms in the universe, you also found that there are assumptions that we made. Okay. I said the sun is about average for the stars in our galaxy. Okay. It's more or less true, but it's not exactly true. Might be off that factor too. Might be, some half the average or twice the average when you count 100 billion stars. And then figure a trillion galaxies around what we think it is. Okay. We'll find out more with the Webb telescope. kind of neat. We're going to start finding out some pretty neat stuff within a year. So with the information, there are about 100 billion stars in the Milky Way. The sun's about average. If you figure, so how many atoms in the galaxy, right? Then figure a trillion galaxies with the Milky Way arm of galaxy being about average. Well, about average. All of a sudden, we could be off by a factor of maybe 10. All right. I don't think it's that far. But, and also, mass of sun is about 10 to the 30th kilograms, okay? Which is fairly close. We can tell that by how far the sun is and how long it takes the Earth to get around it. Okay, a little bit of physics. All right, now, taking off on where we've gone and where we've been. I think we're focused. We'll look clear. We start off, everything kind of goes back to systems and equations, as I've tried to emphasize. Okay. And let's emphasize linear equations. Okay. So when I say equations, I mean linear equations, because that's the only thing to deal with in this course. M equations and n variables you can solve. By Gaussian elimination. Okay. Now let me digress. Can't help myself, I'm sorry. Reading a book titled The 10 Equations That Rule the World or something like that. And pretty good stuff. And most of the equations I more or less understand. There's one that takes some pretty sophisticated analysis. But most of them are pretty simple. And one in the chapter that I'm on right now, which is about midway through the book, is Markov chains. And we did that. I did the same genetic thing. Now, I often, when I do a quick summary of this course at the beginning to give people perspective, which I'm not doing this term, I'm still using WebAssign, which I have a love-hate relationship with, okay? But y'all are apparently using it appropriately, which convinces me that it can be used appropriately, okay? And when used appropriately, it's a good tool. I think the problems are too easy. I mean, you need easy problems. It doesn't have any really challenging problems. It doesn't have problems. It actually causes you to have to write things out and really analyze, okay? I think you all are capable of that, and I'll probably challenge you with a little bit of that later in the course. Anyhow, I often do a summary, and I've done this with governor's school. In the summer, I did governor's school program every summer for 30 some years. Get some pretty good high school students. And a few that really shouldn't be there, but who try. Try to serve them while we still challenge the best. Okay. I had one a few summers ago where I really did a lot of stuff in linear algebra, where we actually talked about why the Markov chain approaches its limit. You do that in terms of eigenvalues and eigenvectors. And I can tell you what eigenvalues and eigenvectors are, but that's coming up, so just wait until we get to it. The thing that set Google on its path, I didn't know this, was Sergey Brin and Page, I don't know what Page's first name is. He hasn't called me lately for advice. Better remind me of his name. Use matrices, Markov matrices, to prioritize pages of the World Wide Web. Okay. And they patented a method that had been around for a long time, but they resurrected it and patented it. They put a certain twist on it, which just uses Markov chains and eigenvalues and eigenvectors, stuff you're going to learn. Okay. So you're going to learn why the Markov chain converges. You're going to have a good picture of it in terms of vectors represented by arrows in R2, which you'll be able to take to R3. It's very powerful stuff, and it's totally behind Amazon recommendations, Spotify, Instagram recommendations you get are coming from Markov chains. Okay, Markov matrices. And it's pretty neat. Well, now that I've digressed, that just gives you a picture of one instance of how powerful this is. Also, if you want to understand quantum mechanics, it's all done in terms of matrix algebra. Okay. If you understand Einstein's theory of general relativity, which is a pretty ambitious goal, I don't. Okay. But I kind of have some of the math behind it. You get tensors, which are like matrices on steroids. And like multi-dimensional matrices. So we don't need to go into the details of that. I'm just telling you that, you know, this course is really the beginning of something very powerful. And you're probably not going to end up, yeah, you might, you know, doing mathematics for Amazon. Okay. I also, one of the preceding chapters, professional sports teams always have professional mathematicians at high levels in the course, all the way up to CEOs, CEOs, general managers and stuff. Okay. So they hire mathematicians. I'm not telling you to become a mathematician. If you're on an engineering track, that's great. Just the other thing I'm getting to is in an engineering, all kinds of applications. You run into it all the time. You really need to understand it. So I don't think you'll need any extra motivation. There's some motivation to excel in this, okay? And in your calculus, which is so back to just kind of an overview of a review, and I'll go into more detail next time when I've had a chance to digest what you responded to and what you're thinking. We have this, okay? We solve these by Gaussian elimination. And the thing that got me on that track is that Gaussian elimination is not a good way to figure out how a Markov chain converges. You have to do the eigenvalue, eigenvector stuff. However, Gaussian elimination is a lot more efficient, for example, for calculating a determinant than anything else. Okay. So I'll just make myself a little note here. This is that. Gaussian elimination is an efficient way to do determinants. It's the most efficient way you have. Of course, for 2 by 2 determinants, it's real easy to just, invert this and change the signs. Okay. Okay. In any case, all I did of M equations and N variables is fundamental. Almost everything we do in this course. I can't do anything right off, but it's not fundamental. Fundamental to the whole topic of linearity, the whole subject, and it gets really big. Okay. If m is greater than n, then you have too many equations for the number of variables. Okay. And I'll say no degeneracy. There's no solution. Now, if I give you 3 equations and 2 unknowns, okay, and one of those equations is not a linear combination of the others, that's really what it amounts to, the sum of multiples of the others, okay, then you're not going to get a solution. It's going to turn out, and fairly soon, you can still often determine the non-solution that works best. And that comes down to a fundamental process. Very important thing is regression, linear regression. Find the best fit line, okay? Or find the best fit quadratic equation. You can do that, and you can understand the method through calculus. You minimize a certain polynomial, or through linear algebra, where you find the closest solution to a situation, which gives you the closest line. We're going to do that. It's one of the big deals. Okay. Kind of a yeah, I'm not finding the right word. It's a big deal. All right. And it also allows you to understand how you do dimensional equations, quadratic, etc. So if m equals m, no degeneracy, you have a unique solution. If m is less than n, you got more variables and you got equations, right? That would be degeneracy. And doesn't matter whether you got degeneracy or not. You're going to get 3 variables, right? Like I would just give you 1 equation and 2 unknowns. 2x plus 3y equals 8. Well, let y equal t, then x equals what is it, 8 minus 3t over whatever the coefficient of x was, okay? Now, I didn't mention if you have m equals n and a free variable and degeneracy, then you're going to get free variables, right? Okay. So I can say, I should have written that down. Okay, so this scheme is pretty fundamental. And it has big implications for linear transformations, as we will see. We'll talk here about linear transformations. I like to talk about linear transformations much earlier. I'm using web design, we're going to probably. And it's going to work fine because y'all are doing the work and you have the great aptitude. It's going to work out at least as well. Okay. So we have that, and that's pretty much what you need to know about systems equations. And so, what else? Well, I'm not going to hit every topic. I don't have enough time right now. We'll fill some stuff in next time. Okay, determinants. They're defined in terms of cofactors. And they can be calculated in terms of cofactors. More efficiently calculated by elimination. Okay. Hard to write that. Something like that. Elementary matrices yield the structure. O matrix. To a non-zero determinant. And you use elementary matrices to prove that elimination allows you to calculate the determinant. Okay. Of course, you got the properties of determinants. Okay, so assuming, of course, that A has non-zero determinant. Okay. 'If determinant of A is not equal to 0, and if determinant of A is 0, you can't do the inverse. So that helps you define singular. Non-singular. And singular. Okay. Determinant ain't zero. Okay. So those are some of the high points with determinants. And they're going to have, again, big implications when we get into linear transformations. Determinant, I think I've mentioned this before, I have or not. You can use a matrix to transform R2. So shapes in R2 are going to change, but straight lines are still going to be straight. So if you got a picture of a house, you can do a transformation that gives you a bigger house, stretches the house this way, tilts the house this way, and stretches it or compresses it in two different directions. Okay? And stretches it and or compresses it. You can stretch in one direction and compress in the other. Okay. So when you do linear transformations, the determinant tells you how much all the volumes change. If any shape, any closed shape encloses a volume, and R2, whether it's by straight lines or curves, to do the transformation on that shape. And well, in the case of R2, it tells you how many times the area you get. And all you're doing is multiplying all the vectors in the space that define that shape. And we'll see exactly what that means. You multiply all the vectors in the space that define that shape. That is, all the vectors whose tips end up on the boundary of that shape. Okay. That gives you a new shape. These vectors are all changing. They change in direction, they change in magnitude. Okay. They're shearing, they're shifting. We'll talk about that. Then again, the new shape will have an area that's determinant of the matrix times the original area. Or in 3 dimensions, it's volumes. In higher dimensions, it's hypervolumes. Okay, whatever that means, because we can't visualize it. But as with most other things, we understand in R2 and R3, visualize in R2 and R3. And then we just use that intuition in higher dimensions, and it works really well. Gives us some guidance as to what we mean and what we're doing. Okay. Okay, well, there's more about determinants. These are kind of some of the high points. Okay. Then we have vector spaces. The properties analogous to those of R2. Okay. You have and when I say properties analogous to those of R2, that's what I wrote down R2, but also R3 that are M. Okay. And we understand that Rn is just collections of all n tuples. Okay. All ordered lists, if you wish, of real numbers. We'll also talk about complex numbers. Okay. That's at the end of the course. And that's really neat stuff. Okay. So vectors and scalars, though, just like in RM, in other words, you can multiply vector by a number. And I should say vectors and numbers, real numbers in RM. You multiply vectors in RM by real numbers. Of course, we understand that. And that gives you properties like, distributive properties and commutative properties, closure, and inverse properties, which are the two biggies. Okay. Usually, if you have a space with closure and inverse, well, okay, subspace is any space that's closed under the operation of the overall space. Because then that implies all the other properties. For example, if it's, well, if it's closed, you got to have the identity. And you got to have that inverse and so forth. And you easily not prove this. Most of those are pretty straightforward. And you should have some idea how that's proved. Okay, subspaces. Compare all the properties. I'll just say the closure is sufficient. Okay. Yeah, there's kind of a set. All the linear combinations of vectors. No, it's not really all linear combinations of the set. It's all combinations of vectors in the set that I didn't want to write out that much. So if we understand linear combinations of the set, meaning linear combinations of vectors in the set, then that's an okay statement. I wanted to make it really clear though, and rigorous. I have all the words in it. Okay, span is all linear combinations of basis. So linear independence. It's the only linear combination. It gives you the zero vector. Is the trivial one where all your constants are zero. Basis. Any. Linearly independent spanning set. And the basis of a given space has the same number of vectors. Which is the dimension of the space. And we just saw the icing on top of the basis thing with the quiz today. So you all performed quite well. I'm change the basis, okay? So there's something of an overview. Other things, like here, talking about elementary matrices, and so forth. We have LU decomposition. And solving equations using LU decomposition, so we certainly want to look at. And a couple of you, I think, listed that. That's always pretty good. Okay. Now let's take another look at your list. I'm still trying to reconcile what you're thinking about with what I'll be thinking about. And actually, it's very close. Everybody's got a good list, and everybody left some things off their list. Okay. Of course, now, looking at what y'all wrote down, one thing that I kind of didn't address, I addressed most of what you got. Okay. Because it's kind of what's obvious when you start thinking about what we've done, and I'm glad that y'all did it so well on that. But the rank is closely related to these ideas. Okay. Somebody wrote down nullity, but it goes right along with rank. Rank and nullity. Closely related to all of this. Okay. In a way that becomes pretty profound. For example, when you try to do regression. So I could mention rank. Is a dimension of the earth space. Voltage is a dimension of the null space. Null space is a big deal. Null space is a set of solutions of AX equals 0. Clearly, all these solutions are in the vector space. Any X, well, all the X's are in the vector space, okay? And if X is a 0 vector, well, it's A times a 0 vector is going to be 0. So the 0 vector is automatically in the null space. If X1 and X2 are in the null space, then since A times X1 plus X2 is A times X1 plus A times X2, you're going to have 0 plus 0, so X1 plus X2 is going to be in the null space. And right away, you see that you have a subspace, right? And it has dimension. And the dimension might be 0. If the only vector that gives you this is the 0 vector, that's it. And of course, that's what you'd have if you had a matrix where M equals N with no degeneracy. You get a unique solution. So any matrix that represents a square matrix with no degeneracy is going to be a unique solution. And also, if M's less than N, you still get solutions. Okay? You still get solutions, but you're going to have a non-zero null space. You get a lot of free variables, a lot of ways to get 0 vectors. Okay. Okay, well, yeah, we're out of time. So that's a good place to close. And we'll review further next time, but do be reading back, making sure you can do pretty much anything that we've asked you to do or that you've been asked to do in WebAssign.